Hello and welcome to the very first video for this channel. So today we will be covering some content. As you can see here, we'll be covering index laws, and we'll be following the new 2019 syllabus for HSC mathematics in New South Wales. But since this is the first video, I want to basically give you a tour of how my lessons are going to pan out. So basically on the left hand side of your screen, you're going to have a sort of PowerPoint slide which gives you basic information about what I'm currently talking about. And then on the right hand side is basically a workbook where I can basically write so that I can do examples or provide explanations beyond what's on the actual slide. So here I just write hello so that you can see that on the right that's what I'm writing, and on the left is what I already have as my content. So basically that's how I'm going to be teaching. And if we now move on to the next slide, I'll basically provide a lesson outline for each video. So this will basically start off with the NESA aim. So basically NESA is obviously the New South Wales Educational Standards Authority, and so they are the ones who set the curriculum in New South Wales. So having this aim tells you basically what you need to have achieved to get that section. So in this part, it's students use index laws and Surds. And so after that, I'll usually write, like I've done here, a flow of today's lesson. So that basically tells you what we're going to be covering. So today, as you can read on your screen, we'll only be covering the first three index laws, and then the remaining part of this NESA aim will be covered in the next two videos. And so if we continue with the flow, I start off with index notation, and then some examples using index notation, and then we move on to finally the actual index laws, the first three, and I'll do some examples on the right hand side of the screen. And finally we have a summary page, which is basically a table of the first three index laws, so you guys can have it for future reference. And so now is when I would basically move on and start the lesson. And so today we'll start with index notation. So we start with the basic idea of a number being multiplied by itself a number of times. So in this case we have 3 times 3 times 3 times 3. So 3 is multiplied by itself 4 times. And so this is equal to 81. And so what I want to get to here is that it's quite long to write this left hand side, so the 3 multiplied by itself 4 times. So index notation basically provides us a nice compact form to write this left hand side of the equation, and then the index laws come out of this, which are basically rules which help simplify indices. So the index notation, just so you start to get a feel for it, is shown on your screen now. So if we have 3 multiplied by itself 4 times, right? So we have the number of repetitions, so it's 4 times, and the actual number that's getting multiplied by itself. And so the actual number that gets multiplied itself we call the base, and that goes here at the bottom. And then the 4 times is the number in which we raise the 3 to. That's how we read it. So we raise 3 to the 4th power. And so I remind you that this is index notation. So as I was saying before, we have special names for each of these parts. So this 3 we call the base. This 4 we call the index. Now on this page, it's basically what I just talked about. The definition here is just a more formal way of showing what I've shown on my workbook, but the terminology at the bottom I think is worth mentioning, that the actual number that it's raised to, so this index, can actually be written can actually be called a power or an exponent. You'll often hear it be called that, but it's also rightly so the logarithm. But I just want to mention it so then it doesn't pop out of nowhere. But I'll be going in depth into that in a later video. So just a heads up. So now we'll do some examples using the index notation. So if we start off with the first question, we have a to the 3. So basically here I'm aiming to convert from index notation to expanded. So this becomes, of course, a, the actual number, so the base, is being multiplied by itself how many times? Well, the index tells me how many times, so it would be 3 times. So it's a times a times a. That should be pretty simple. Then the second one is we want to convert it to index notation. So we have 3 multiplied by itself 3 times. So we have the base of 3 multiplied by itself, so this is 3 times, so the power is 3. And then multiplied by 4, the base, multiplied by itself twice, so squared. Notice how we can't get simpler than what I've written on the right hand side. So we can't unify bases. Bases just can be simplified if they're the same. And that's basically your index laws almost exclusively for the same base. So watch out for that. And then finally, I need more space for this final one. So bear with me while I clear up the space. 3, so question 3, we have c to the 3 times c to the 5. So basically to work this one out, since we don't have any index laws to work with, we can just expand it. So we have c times c times c. So we put parentheses just to separate them, so we can keep track of all the c's. And then if we do c to the 5, so this would just be c multiplied by itself 5 times. And so now here we have a long expanded form of what's written at the top. But of course, the parentheses aren't really doing anything. They're just telling us where each of the terms came from. So really, they could go away, and we're just left with c multiplied by itself, and in a moment, we'll count them out. But of course, this should just be 1, 2, 3, 4, 5, 6, 7, 8 times. So this becomes c to the 8. So the reason I did this example is because I want you to realize that this 8 appears to be the sum of these two initial indexes. So we have 3 plus 5 equals 8. And so basically, is a question for you, is this just a one-off? Were we just lucky to get this? Or does this apply in general? And so this is the idea that basically leads to the first index law. And so that's what we'll cover right now. So the first index law, I call it the multiplication law, basically tells us that if c, d, and e are all real numbers, then if we have c raised to the d power multiplied by c raised to the e power, then this is equal to c raised to the sum of d plus e. So, of course, I've provided some examples so we can get some practice, because when we have just pronumerals, sometimes it's a bit hard to get a grasp of what's actually going on. So with numbers, it's a lot easier. So for the first question, so we have 1 there, 3 to the power of 3 times 3 to the power of 6. So this law is telling us that as long as the bases are the same, which in fact they are, it's 3 and 3, then if we multiply them together, then the indices at the top just add up. So we get 3 to the power of 3 plus 6, which is 3 to the power of 9. Good. So now we have the second question. So 6 to the 4th power multiplied by 5 to the 7th power. Well, here we have different indices. So here's one index of 6 and this one's 5. But they're not the same. So we can't use the multiplication rule. So in fact, the simplest form of this expression is really how it's written out. Because if we were to expand, that would be the opposite of what the question's asking. So we just leave it how it is. Good. question 3. We have a to the 4 multiplied by b to the 6 times b squared. Notice how when it's raised to the 2 power, I call it squared. And then if it's raised to the 3rd power, you can call it cubed. That's just special names they have for those numbers. So for this question, the best thing you could do is collect like terms. So when we collect like terms, we're basically getting the bases together. So we get a to the 4th power multiplied by a to the 7th, and then put it in parentheses so we can keep track of it, multiplied by parentheses again, b to the 6th power times b squared. And so this is just equal to, well, using our law, we have a to the 4 plus 7, multiplied by b to the 6 plus 2, which of course is equal to a to the 11th times b to the 8th power. Good. So if I now just rub out the top so we can rub out the whole thing while we're at it. And now we do the last question, which is a bit more difficult, but shouldn't be too bad. We have 3 to the 1/2 power times 3 cubed. So even though for now we haven't covered fractional indices, so they might be a bit strange to you, but really we don't really need an interpretation of this right now. For now we're just being asked to simplify. So if we just basically blindly apply the law, we get that 3, the same base, these are in fact the same base, and then we add the indices. We have 1/2 plus 3. So this is just 3 raised to the 3.5 power, which is, you could also write it as 3 to the 7th over 2 power. We don't really need an understanding of what this means, but this is the simplest form. So we've done our job, and we'll be covering fractional indices in the next video. So don't worry too much about this for now. I just wanted to make sure that even though you don't have integers as your indexes, you can just apply this law. So yeah, that's that. So basically that was the first index law. It's quite a simple law, but everything basically flows out of this law. For those who want proofs, I will be providing them in a different video dedicated for proofs for the index laws. So look out for them if you want any of the proofs for any of the index laws. So now we move on to the second law, the one I call the division law. And so it's basically kind of the opposite of the multiplication rule. So if we have C, again, C, D, and E are all real numbers, and C to the power of D is divided by C to the power of E, then we can simplify this as C to the power of D minus E. So again, we have some examples which help us to understand this. So if we do the first question, which is 3 to the 5th power divided by 3 squared, well, according to the law, this was simply as 3 to the 5 minus 2, which is 3 cubed. Now, I want to prove this a bit more to you guys. So you just don't just accept the law. I'll try to give you more of an intuition as to why it works. So here, if we expand, so we have 3 to the 5 is of course 3 multiplied by itself 5 times. And so we divide by 3 squared. Now of course, here we can just cancel some 3's. If you don't see this directly, you could split this fraction up into 3 times 3 times 3, and then multiply it by 3 on 3, and multiply it by 3, sorry, that's a 3 on 3. And so 3 on 3, it's just 1, so this is 1, and so is this one. So you're just left with 3 times 3 times 3, which of course is 3 raised to the 3rd power. I could have just cancelled from the start, but I hope this second line, this one here, this third line, sorry, makes more sense. And basically we're cancelling terms, which is why we just reduce the index by subtracting the two initial indexes. So that was the first question. If we now move on to the second one, this one is a bit trickier, but again, bear with me. So we have a squared divided by a to the fifth. So according to the law, in this scenario, we simply do a to the 2 minus fifth to the 5, which is a to the minus third power. Now, this is where things get really weird. What does a being raised to the negative power actually mean? I won't answer it right now, because we do need to cover negative indices, which I will do in the next video. But for now, we've simplified it, so we've done our job. We don't really need to understand what this means, but it does have a meaning, more than I can give you right now. So just accept it for now. This is how we're just applying the law now, but I will give you a better understanding in the next video. So make sure to watch that after this one. So if we now do the third question, we have 6 to the 4th power multiplied by 6 squared divided by 6 to the 6th. So here we're combining the multiplication and division rule. So we're kind of building our knowledge. If we now do this by parts, we can collect the similar bases here, and using our multiplication rule, we add up the powers and then leave this as divided by 6 to the 6th. And so this is 6 to the 6th power divided by 6 to the 6th. Now, instead of simply here, because 6 to the 6th divided by 6 to the 6th is obviously 1, because any number divided by itself is 1. But instead we're going to apply the division rule. And this, I'll explain why I did do this. So we get 6 to the, so using our division rule, it's 6 to the 6 minus 6 power. So it's 6 to the 0th power. But we've obviously found out that it's 1. So we find that if we raise 6 to the 0th power, it's equal to 1. And so basically I wanted to start to introduce the idea of weird numbers as your powers. So the second question had a negative power. This one has the power of 0. So all of these do have explanations, and again, I will explore them in the next video. But for now, we've found our answer. We've applied the division rule, the division law, and we're basically done for now. But I think it's worth mentioning how interesting these results are. And finally, let's cover the last one, which is what I like to call the power of a power law. So the power of a power law is basically when you have a base, so a number just raised to a number, and that whole thing is raised to another number. So we have, again, C, D, E are real numbers. We have C raised to the D power, and then raised to the E power. And then this law tells us that to simplify this, this is just C raised to the D multiplied by E power. So let's do some examples to get some practice and to understand what this means. So we get 3 to the 3rd power or to the 7th power. So using our law, this is 3 to the 3 plus 7th power, so 3 to the 10th. Now, again, I'm not providing a proof for this law, but you can imagine that you can think of it for a while and it kind of makes sense, as long as you have positive integers. So here we have packets of 3 cubed being multiplied by itself. I'm going to run out of room, but packets of 3 cubed multiplied over 7 times. And those 3 cubes themselves are 3 multiplied by itself 3 times. So of course it's just logical. So if we were to expand this a bit more, so you get an idea. So you get packets of 3 multiplied by 3, so 3 times, and so this goes on. And so this is 7 times. So in total, the amount of times 3 is multiplied by itself would be 3 times 7 times. So, I've actually made a mistake here. This should be times. So 3 to the 21. So this is 3 to the 21 power. So that's basically a kind of a pseudo proof, if you want, for why this power works. But again, this is limiting ourselves to positive integers as our powers, and it does apply for all real numbers. So now we move on to the second question, which is a half raised to the 6th power raised to the -1 power. So again, -1s creep up, but let's just apply the law and get an answer. So according to our power law, power of a power, this is just a half raised to the -6th power. So we're done. No need for further explanations. I will be covering this more properly in the next video. Just, I want to provide you with a wide range of examples so that you're able to apply this law anywhere. And then question 3 is a cubed to the 21st power. So obviously here is, I provide this one because imagine having to write this out in expanded form. So you have groups of a cubed being multiplied by themselves 21 times. So if we use the power of a power law, we see that it's actually a to the 63rd power, which is, and sorry, I should have put in that it's 3 times 21, which is what our law is telling us. But that's a ridiculous amount of times to write a multiplied by itself. So this notation is very useful for writing very long and repetitive chains of multiplication. So these index laws provide us a way of getting to this simplified form without ever having to expand and write all that out. So basically those are the 3 laws. They're quite simple when you have simple questions. When you start to get weird numbers like -1 as your powers or fractions, it starts to get weird because the general intuition of just multiplying the same number over and over kind of dissolves and doesn't really work anymore. But we'll get into more detail as to why that's so in the next video. For now, those are the 3 laws, and so now here's where this part of the video is where I provide a summary. So here I've provided a table with the 3 laws we've covered, the description, so what I've called them, the multiplication, division, power of a power law, and then symbolic representations to it, so basically what they are in maths terms or in maths symbols. So keep that, memorize it, because it's very useful to know these laws, and they provide the foundation for key topics later on in mathematics. So these are really important to make sure you understand. So the next video, which covers the next index laws, will come out shortly. So that you know when the video comes out, make sure you subscribe and become a curler. I hope you've enjoyed my video today. If you have any feedback, any recommendations, obviously this is my very first video ever, so there's probably heaps of things that people have noticed that could be better. So leave them in the comments, and I'll be sure to read them and implement them into my future videos. So these videos are for you. So tell us what you want, and I will make a difference and try to help you out. Also, if you have any specific questions, math questions that you want me to work out, send them through in the comment and I can make a dedicated video for it, or I can send you a message. We'll see, we can work that out. Anyway, thank you for watching and have a nice day.